Hey, this week we will be talking about Newton's laws of motion, and there's Newton right there. And this is a great picture over here. This kind of sums up Newton's laws of motion right here. If you think about the idea of what's going to happen if this guy goes this way and this little guy goes this way, and obviously they have different weights to them, and the amount of force that they have behind them and things like that, and the way that things are going to move and all that kind of stuff. If you just kind of think about those different ideas, that pretty much is the idea of Newton's three laws of motion. As usual, remember that red slides mean you have to take notes. You should have your Inner Planets handout to go along with this, and don't forget to look for the owl. At the end, make sure you tell me where the owl is and summarize what you've learned in a few sentences. So Newton's first law of motion is something that you may have heard of before, and that goes, an object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Well, it's a really long sentence. That's kind of a mouthful. But basically, to sum that up, basically what that means is that objects keep doing whatever it is they're doing unless you make them change. So if an object is moving, it will keep moving in exactly the same way. And we want to think of the ideas of speed and direction here. So an object will keep moving in whatever direction it's going in at that same speed unless you make it change. Now, the first part of that says that an object at rest tends to stay at rest. That's the same idea. It's just its speed happens to be zero and its direction happens to be zero. So it's the same idea there. It's just going to keep doing what it's doing unless you force it to do something different. And that's the acted upon by an unbalanced force part at the end there. You actually have to make it change direction or make it speed up or slow down. Otherwise, it will basically just keep doing whatever that it was doing. So this is a good way of thinking about it. We have a soccer ball here, and that soccer ball is an object at rest, and unless you do something to it, it's just going to kind of stay there. It's not going to do anything. We have to apply a force, in this case, kicking the ball, right? And that will make the ball change its movement. It will make it go from being at rest to moving, and then that object will keep moving, and it will want to keep moving in the same direction, kind of straight ahead at the same speed, unless it's acted upon by an unbalanced force. In this case, the ball is going this way, and the unbalanced force is the net stopping it, making it stop. So you have to force something to stop, okay? You have to force something to start moving. This is a good example here. If you look at the passenger in this car, the dummy that's driving the car here, you can see that when the car crashes into the wall, the passenger wants to keep going forward. That's the same thing that you've experienced when your parents hit the brakes when you're in the car and things like that, and also a great reason to wear your seatbelt. So this is known as the law of inertia because that's basically what inertia is. Here's another good example here. Obviously, this guy's bike stopped, but he did not stop. He is an object in motion that wants to stay in motion. And that's basically what the idea of inertia is. Inertia is something that resists a change in motion. So think about the idea of this strong man here trying to pull this jet, and think about if you were in that position trying to pull this jet. This jet has a lot of inertia because it's so heavy. So you can imagine that inertia is related to the mass of an object or how heavy it is, right? The more heavy it is, the more inertia it has. It's very difficult to get this airplane to get moving. In the same way, it's very hard to get this ball in Indiana Jones here. It's very hard to get this ball to stop moving. So it's hard to get an object to change whatever it is that it's doing, especially if that object is really heavy. So this guy here, this is kind of a fun one. This guy here might be wondering, so why don't I just keep going in this situation? Why did I stop so quickly as soon as I hit the ground? Well, you may know the answer to this. The answer is friction. So friction is basically a force that we encounter pretty much everywhere when we're on Earth. Things are very different if you're in space. In space, there isn't any friction and there isn't any gravity and things like that. And those are forces that are sort of always there for us. So we kind of feel like when you push something, it automatically slows down, or when you throw a ball, it's going to kind of start, it doesn't really go in a straight line. It starts to move towards the Earth. But that's because there are forces acting on it, the force of friction or the force of gravity, things like that. So in this case, friction slows an object down until it stops. Friction basically takes that kinetic energy and turns it into heat energy. And it can also wear an object down, like the head of this match or the soles of your shoes or things like that. Okay, Newton's second law of motion. For Newton's second law of motion, we have the relationship between an object's mass, m, and its acceleration, a, and the applied force, F. This is a relationship between these different things. Its mass, its acceleration, and we'll talk about that in a second, and a force that is applied. Okay, and this is one of the few formulas that I'll give you, and the formula is force equals mass times acceleration, or F equals ma. Okay, so let's make sure you understand these things. A force is a push or a pull on an object, simple enough. Mass is the amount of stuff that something is made of. We've talked about that before. And acceleration is a change in movement, meaning a change in the speed or the direction. You might think of acceleration as being speeding up, like a car accelerating. But in science, acceleration includes speeding up, but also slowing down and changing direction, so turning left or right. So any sort of change in movement at all, any way that you're changing movement is what we call acceleration. This is a good way of thinking about Newton's second law of motion. Think about the difference between a real car crashing into something and a toy car crashing into something, right? These are kind of similar ideas. We have a car crashing into a pole of some sort in both cases, but you can imagine that there is a lot more force with the real car because there is a lot more mass. There is a lot more acceleration going on with the real car, and so therefore there is a lot more force going on with the real car. So just think of it in those kind of terms. And remember, all three of these laws are kind of related to each other. So this goes back to what we were talking about before, this idea of inertia. The more mass something has, the bigger and heavier it is, the harder it is to get it to change its movement in some way, to stop or start. Let's talk a little bit more about acceleration. This is a great picture of a space shuttle trying to accelerate away from the Earth. So acceleration is the rate of change in velocity. So velocity is kind of like speed, but it's speed and direction. So it's how quickly you are changing your speed or changing your direction. That's what acceleration is. And I have one more formula for you here. Acceleration is the final velocity minus the starting velocity divided by time. It's a fairly simple formula here. You just take how fast was it going at the end of the race, how fast was it going at the beginning of the race, and then you divide that, you subtract those, and you divide it by the amount of time that it took to get from the start to the finish. We'll practice some of those in class. Now, Newton's third law of motion. We can see this nice animation here where the cannonball goes one way and the actual cannon goes the other way. I think you can kind of imagine that idea, especially if you've ever shot a gun before or see somebody shoot a gun, right? There's that kickback of the gun. The gun tends to go backwards towards you while the bullet goes forwards away from you. So Newton's third law, you may have heard this one too. For every action, there is an equal and opposite reaction. Think of something like a balloon, right? So the air rushes out one way and the balloon goes the other way, right? For every action, there is an equal and opposite reaction. All right, so those are Newton's laws of motion. Nice and neat and easy. We'll work on those all week. So we have Newton's first law: an object in motion tends to stay in motion, and an object at rest tends to stay at rest. And remember, think of that as just the idea that objects want to keep doing what they're doing, which is basically the idea of inertia here. Whatever their current speed and direction is, otherwise known as velocity, whatever their current velocity is, that object will want to keep doing that. Newton's law, first of all, is a relationship between force, mass, and acceleration. And so you should know what all those words mean. And the formula there is F equals ma, and acceleration is just a change in movement, slowing down, speeding up, or changing direction. And we have our next formula here, which is acceleration equals the final velocity minus the initial velocity divided by time. Again, we'll practice some of those in class. And Newton's third law of motion: for every action there is an equal and opposite reaction. We'll have fun experimenting with all of these in class, and I'll see you then.